This video explores a bridge between the visible chaos and the invisible atomic order. Brownian motion, the jittery, random movement of microscopic particles, provided the physical link needed for Albert Einstein to find a way to weigh the invisible. This phenomenon, known as Brownian motion, can be observed in gas, suspensions, and emulsions. It involves a continuous, erratic jiggle of particles. Larger fat globules jiggle less, while smaller casein micelles jiggle more vigorously, illustrating this universal motion. When Robert Brown first analyzed this motion, he needed to rule out the possibility that the movement was biological. His control experiment, using particles trapped inside ancient quartz crystals, showed the jiggle was physical, not biological. The jiggling particles are suspended in a sea of atoms, moving at incredible speeds. A suspended particle is constantly bombarded by the surrounding medium, experiencing approximately 100 trillion collisions per second. On the macro scale, molecular collisions cancel each other out, resulting in no movement. However, at the micro scale, the randomness creates an imbalance of force, which drives the particles jiggle. This interaction can be modeled with a tray of small ball bearings and a larger plastic bead. The ball bearings move frantically, kicking the plastic bead, which moves slowly and randomly. If the ball bearings were invisible, the bead would appear to have a life of its own. In 1905, Einstein assumed that visible particles and invisible atoms follow the exact same physical principles. This bold assumption allowed him to use existing physics equations to derive a formula for the quote-quote diffusion coefficient, measuring how fast a substance spreads through a fluid. Brownian particles engage in a random walk, moving a random distance and direction over fixed time periods. Einstein realized that by observing and measuring how far these particles travel on average, the quote-quote jiggle could be converted into usable data. Einstein's final equation related measurable properties, such as the diffusion coefficient, temperature, viscosity, and particle radius, to Avogadro's number. By measuring the wobble or diffusion, scientists could solve for Avogadro's number. 3 years after Einstein's paper, Jean Perrin meticulously tracked the motion of gum resin particles to test the theory. His calculations confirmed the existence of atoms and earned him the Nobel Prize. Avogadro's number acts as the conversion factor between the macro world and the atomic world. By dividing 1 gram of hydrogen by Avogadro's number, we can find the exact mass of a single hydrogen atom. Einstein and Perrin gave us the scale to weigh the atom. A surprising property of gases is that volume is independent of atomic weight. Equal volumes of gas contain the same number of molecules at a specific temperature and pressure. This reinforces the fundamental nature of the constant that Einstein and Perrin measured. 1905 is known as Einstein's Annus Mirabilis, or miracle year. He published pivotal papers on relativity, the photoelectric effect, and Brownian motion. While relativity is famous, the Brownian motion paper was the one that finally convinced the scientific community of the physical reality of atoms. Brown, Einstein, and Perrin looked at the chaotic jiggling of microscopic particles and discerned a profound truth. They turned a microscopic wobble into one of the most significant measurements in science, proving we can weigh the atom by understanding the noise.